Hello, I'm Scott, and this is my first of a two-part series on trigonometry and graphs of sine and cosine. Trigonometry is taught in high schools and colleges around the world and has some amazing uses. Astronomers use it to triangulate the position of stars by looking at them with different telescopes. And engineers and roboticists will use trigonometry to develop computer models of their machines, so they can see how they will respond to different stresses and pressures. Trigonometry is even used in video games to render a three-dimensional model to a 2D screen. And trig is simply essential to our modern understanding of light and the physics of how it moves in waves, and electricity as well. The thing is, though, trig gets a pretty bad rap. I bet you know people who came out of high school saying, I hated trigonometry. It made no sense. The class was boring and confusing. These are issues that I want to try and clear up today. So let's do some trig the right way and see how we can graph the different trig functions better. Let's first clear up a few points on this video. The first one is that I am expecting you to already have some understanding of the triangle representation of sine, cosine, and tangent. In your trigonometry class, you've probably been taught SOHCAHTOA and about how the sine of an angle is its opposite over hypotenuse and some various other representations for cosine and tangent. So, once you've already gotten past that part in your trigonometry class, your teacher will probably come along and say, okay, now we're going to talk about the graphs of sine, cosine, and tangent. Now, you might think to yourself, well, that should be pretty simple. They're not that complicated of functions. But then when you actually go to Desmos and plug them in, you get weird stuff like this. Like look at this. This isn't triangular at all. It's a weird up and down wavy thing. It's green for some reason. Why would I want it green? No. Red. Though that has nothing to do with the function. And then it has like pies in here and stuff. What the heck is pi doing there? It doesn't make a ton of sense out of the box to most people. And it gets more confusing when you plug in cosine. Cosine, now that's the sine, but shifted over. And it's intersecting at pi over 4. What? It's very confusing if you just look at it this way to begin with. So what we're going to do is we're going to kind of take a step back and we're going to forget everything we know about the triangle representation for a while, okay? Just throw that all out of your mind and come along with me as we look at how we might get to this wave function by working backwards. So we can look at some clues to the shape of this function in order to figure out how we might represent it. We can see that as we zoom out, the same pattern keeps getting done over and over again. So that could be a clue to us that we want loops and cycles to be included in our representation. And it's very smooth, not jerky at all. So we want something to create it that's smooth. And then it also has pies involved all over the place. So we want something that has to do with pi. If you hadn't guessed yet, we're going to use a circle to represent this. Because it moves up and down, what we're going to do is we're going to take a circle and we are going to plot the up and down motion of a point on that circle in order to generate this function. I've already done that for you, so you don't have to go through the trouble of building or coding anything. And here we can see that we have a circle that's turning around, kind of like a wheel. And there's a point on it that moves. This measures the height of that point and just moves up and down with it and traces out this wavy shape. You're going to have to trust me on this for a little bit because I'm not going to explain it fully at the moment. We're going to journey there. But this shape is actually the same thing as sine. Take a few moments just to kind of watch it roll out and get kind of an intuitive feel to see, yes, this circle turning around does create the same shape that I saw on the Desmos graph. Okay, so the next thing that we are going to work on is going to be trying to take the sine function and show that it is the same thing as this rotating point on the circle. The stickler point is, though, the thing that we use as an input for our sine function is an angle, right? 15 degrees, 20 degrees, 30 degrees, 90 degrees if you're crazy, though with the triangle that doesn't make a ton of sense, you know? But here, on our representation, the only thing we have to go off of is distance turned, how far this point has moved around the circle so far. Now, we will go over how those two things can actually be united so that the distance turned and the angles are the same. And for that, we're going to have to use some pen and paper. So let's go to that. At its core, the sine of a right triangle is really just a function. A function is something that takes some input and then outputs an output. So let's look at what our function sine of theta is doing for inputs and outputs. It's taking some angle as its input in degrees and then outputting a ratio, opposite over hypotenuse. Then our circle representation, where we have a point moving around the circle and then we look at its height, takes a distance, namely the distance that point has moved around the circle, and then it outputs another distance, namely the height of that point moving around the circle. Now the question is, how can we make these the same? First, let's try and make the input of the sine and our circle the same. Make the angle and circular distance the same. We'll use something called the unit circle, which is a circle centered on the plane's origin with a radius of 1. Now, if we take some angle theta and put it at the center of our unit circle and see where it intersects that circle, we now can represent theta, that angle, instead of being degrees, being that arc length of the intersection. This works because the unit circle is uniform for all possible values of theta. If we take this different representation, then pi over 2 is now 90 degrees, and pi is equal to 180 degrees, and 3 pi over 2 is 270 degrees, and 2 pi is 360 degrees because of all the different representations of ratios of the circumference of a unit circle. This different way of representing angles is called radians, and it kind of helps to just look at it for a while and just kind of make that mental transition of we're not using degrees anymore, but we're using these arc lengths because that will help us in unifying the triangles and the circles to understand these waves. Now that we have unified the angle and the distance inputs for our two different representations using the radian measure, now is the time for us to unify the outputs. If you remember from just a little bit ago, the output of our sine function is a ratio, and the output of our circle thing is a distance, namely the distance from this center point here. In order to unify these, we are going to finally show a triangle on our circle. So we're going to move away from this simulation here and go over to a Desmos graph that I have prepared for you guys. So here we have essentially the same thing, but it's our unit circle this time. We have the circle and it's centered at the origin, and if you see, it has a radius of 1 there. So we have our point, and what we can do to get a triangle is first we want our hypotenuse. We can do that by drawing a line from the origin here out to that point. And if I turn that on, then you'll see here we have this line going out, and that gives us our hypotenuse. And then if we draw a line from the point down to the bottom, suddenly there's a triangle. There's a right triangle for us. And then we can use that length there as the bottom. That's the other side, and then that's the hypotenuse. This angle here can be theta. And if you remember from earlier, any angle that we put here, that distance right here is its measure in radians. So now we have a triangle that has a right triangle that has theta both as this internal angle and theta as the distance this point has moved from its starting point right here at 1, 0. So if we can show that this height here of the point, so this length on this side, is equal to sine of theta, then we will have shown that the triangle representation and the circle representation are the same, and we know where the waves come from. So let's go right over to that. So if we want to solve this problem, we're first going to need our unit circle. So we take our plane, and the circle is going to be at the origin of that, and it'll have a radius of 1, right? Now, if we put our point on there, we can draw the triangle that we made. And then we can make sure that that inside angle, theta, is what we're focusing on. Now let's try and figure out sine of that. We know the hypotenuse is 1, and that opposite side, let's call it s, is the height of our point. So sine of theta is s over 1, or just s. What that means is that the height of our point, or s, is equal to sine of theta, which unifies height on the circle with our point rotating and the sine function. Now, what you're probably wondering about is cosine. I've talked about sine for this whole video, but haven't really mentioned cosine a lot. If you remember, cosine looked just like sine, but just kind of shifted over. That might clue you into the fact that cosine is kind of like sine, but just shifted around a bit. So, what we can do is we can look at our opposite side there well, not our opposite side, the adjacent one. Let's call that adjacent side C. So, cosine of theta is just adjacent over hypotenuse. And since our hypotenuse is 1 and our adjacent is C, that means C over 1 C is cosine of theta. So that means the x component of our point on the circle is cosine, and that unites those parts. So now we know that cosine and sine both have representations on the unit circle linked to a triangle. And here we have the sine in red and the cosine in blue components moving along with our point as it rotates around. And you can see how we can still draw that triangle on any quadrant of the circle that the point moves to. It really helps to just watch these play out for a while and get a feel for why sine and cosine are what they are at different points, why the waveforms come out. So in the description, you will find links to both this simulation here and to this Desmos graph. I really hope that this video has helped you guys to get a better feel for how sine and cosine work. In the next part, we will be going over my favorite part of sine and cosine, how they change when we change the speed of the circle's rotation. I'll see you guys there.